Good day, my name is Sarah May S. Santos. I am from BSc S3A. So the problem that was given to me is to analyze regularity of the language that all strings start with 0 or more A's and end with an even number of B's. Let's describe the alphabet and the language. For the alphabet, we have A, B, and for the language, it consists of strings that begin with 0 or more A's followed by an even number of B's, including 0. So here are the example of strings that are valid or accepted in the language and invalid or rejected strings in the language. For the valid, we have an empty string. Since it is 0, it is an even number, so it is accepted. Next is A. Since it consists of 0B, which is an even number as well, it is accepted. Next is ABB. Since it consists of 2B's, which is an even number, it is accepted in the language. Next is AABB. It consists of 4B's, which is an even number, it is accepted. Next is BB. Since it contains 2B, which is an even number, it is also accepted. Next is AAA. Since it contains 0B, which is an even number, it is also accepted. And last, AAA since it contains 4B's, which is an even number, it is accepted. And for invalid, we have AB. Since it contains 1B, which is an odd number, it is rejected. Next is AABBB. Since it contains 3B's, which is an odd number as well, it is rejected. So the number of A's doesn't matter at all. What matters is that the number of B's must be even. So any string with an odd number of B's is not in the language. Now let us discuss the Myhill-Nerode theorem and how we are using it to test the regularity. The Myhill-Nerode theorem states, a language is regular if and only if it has finitely many equivalence classes under the relation. The strings x and y are equivalent with respect to the language L if and only if for all possible strings z. The concatenation of x and z is in L if and only if the concatenation of y and z is in L. In simpler terms, for a language to be regular, there must be only finitely many ways to distinguish between strings with respect to how we can extend them and still stay in the language. Now let us try to identify distinguishable strings using the Myhill-Nerode relation. Let us consider these two strings. X sub 1 is equal to A, x sub 2 is equal to AB. And let's define distinguishing string to Z is equal to B. For the solution, we will get the value of x sub 1 Z. So the value of x sub 1 is equal to A, so we put A. The value of Z is equal to B, we put B. Now we have an AB string. Next is we get the value of x sub 2 Z. The value of x sub 2 is AB, so we put AB. And the value of Z is B, so we put B. Now we have an ABB string. Now to visualize the problem, we will be using a state diagram. The Q0 represents the even number of B, and the Q1 represents the odd number of B, and the Q2 is the trap state. Now let us try first the AB string. So for the input A, we go to Q0 itself, and for input B, we go to Q1. Since Q1 is not an accepting state, and the string contains only one B, which is an odd number, it is rejected. Next is ABB string. So for input A, we go to Q0 itself. For input B, we go to Q1. And for input B again, we go to Q0. Since Q0 is an accepting state and the string contains 2B, which is an even number, it is accepted. Therefore, x sub 1 is not L equivalent to x sub 2 implies that these are distinguishable. In conclusion, the language is regular. This is because the number of A's in a string has no effect on whether the string is in the language. It can be any amount, including 0. The only actual constraint is that the number of B's must be even. This condition is simple and can be easily checked using a finite automaton that keeps track of whether the count of B's is even or odd. Such tracking requires only two states, one for even and one for odd, toggling between them with each B. Since a finite automaton can be built to recognize the language has a finite number of equivalence classes under the Myhill-Nerode relation. Therefore, by the Myhill-Nerode theorem, the language is regular. That's all for the Myhill Nerode problem. Thank you for watching.